This is wild. It's so strong that it hurts. Yeah, see my thumbs?
Today, we're going to be taking a deep dive into one of the most advanced 3D printing materials on the market, carbon fiber reinforced polyether ether ketone, or CFP. This is a high-performance thermoplastic composite known for its incredible strength, thermal resistance, and chemical durability, making it a top choice for industries that demand the best. So what exactly is CFP? CFP is a composite material made from polyether ether ketone, a high-performance polymer reinforced with carbon fibers. These fibers can be short or chopped, typically making up to 10 to 30% of the material by weight. This combination results in a material that offers outstanding mechanical, thermal, and chemical properties. CFP is part of the ptfe family of polymers, known for their excellent stability in extreme conditions. By adding a carbon fiber, you get a material that's not just strong, it's exceptionally stiff, lightweight, and resistant to heat and wear. Now, let's break down the technical specifications of CFP and what makes it such an impressive material. Tensile strength, up to 105 megapascals. This means CFP can withstand high levels of tension without breaking, making it ideal for load-bearing applications. Tensile modulus, 8100 megapascals. This is a measure of stiffness, meaning CFP maintains its shape even under stress. Flexural strength, 136 megapascals. This measures how well the material can withstand bending without cracking. Flexural modulus, 8300 megapascals. A high flexural modulus means that CFP is extremely rigid when subjected to bending forces. Heat deflection temperature, 265 degrees Celsius. This is the temperature at which CFP begins to deform under load, making it highly heat resistant. Density, 1.39 grams per cubic centimeter. Despite being dense, CFP is actually much lighter than metal alternatives while maintaining impressive strength. CFP has a surface resistance of greater than 10 to the power of 9 ohms, making it suitable for ESD-safe applications. So how does CFP compare to regular PEEK? While both materials share the same PEEK base, adding carbon fiber dramatically enhances performance in a few key areas. Regular PEEK has a tensile strength of around 100 megapascals, but CFP can achieve up to 105 megapascals, 5% improvement. The carbon fibers give it added rigidity and strength retention under load. Regular PEEK has a tensile modulus of 3,720 megapascals, while CFP jumps up to 8,100 megapascals. That is more than double the stiffness, making CFP much better for applications where maintaining shape under stress is critical. Regular PEEK has flexural strength of 130 megapascals and a flexural modulus of 2,700 megapascals. CFP offers a 136 in flexural strength and 8,300 in flexural modulus, far stiffer and more resistant to bending. Regular PEEK has a heat deflection temperature of 140 degrees Celsius, while CFP can handle up to 265. This makes CFP much more suitable for high temperature environments. Regular PEEK has a density of 1.3 grams per centimeters cubed, while CFP is slightly denser at 1.39 grams cubic centimeters due to the additional carbon fiber. This means a little bit of added weight, but the performance gains outweigh this minor increase. CFP is used in some of the most demanding industries, and its performance has led to breakthrough applications across multiple sectors. In aerospace, CFP is used for high-strength brackets, fasteners, and engine components, but it's not just about the strength. CFP is also lightweight and maintains performance under extreme temperatures. In one case, CFP was used to create satellite brackets where its strength and thermal resistance allowed for lighter components without sacrificing durability, increasing payload capacity. CFP shines in high-performance automotive applications, most notably in motorsports. A standout example of this is its use in the Visa Cash App Racing Bulls Formula 1 team's brake cooling ducts. These ducts, produced using Robosi's CFP and 3D printing technology, provide enhanced thermal management and reduced weight without sacrificing strength. This breakthrough allowed the team to cut production costs by 68% and reduce production times by 66%, all while maintaining precision and reliability on the track. Imagine the same technology applied to high-performance street cars where lightweight strength can enhance fuel efficiency and acceleration. CFP has also transformed orthopedic and spinal implants thanks to its radiolucency, allowing for clear imaging in both X-rays and MRIs, and its bone-like modulus, making it an ideal material for spinal cages and bone fixation devices. But that's not all. CFP is also used in patient-specific surgical guides and durable surgical tools, providing strength and sterilization without the weight of metal. In the electronics industry, CFP is used for wafer handling, ESD-safe fixtures, and precise connectors. Semiconductor manufacturers use CFP for robotic arm grippers and test sockets that must maintain precision and stability even at high process temperatures. CF Peak excels in industrial settings where high-load bearings, bushings, and chemical-resistant components are required. In chemical processing plants, CF Peak is used for pump and valve components that must resist corrosive chemicals and maintain strength at elevated temperatures. Imagine a pump running caustic chemicals without the risk of corrosion or mechanical failure. When it comes to printing with CF Peak, setting up your printer correctly is crucial. Here's what you need to know. Nozzle temperature, between 390 and 450 degrees Celsius. CF Peak requires extremely high temperatures to properly melt and flow. This is because Peak itself has a high melting point and the carbon fibers increase the thermal conductivity, requiring precise control. Bed temperatures, between 70 to 140 degrees Celsius. A heated bed helps maintain adhesion and prevents warping, ensuring that your parts stay flat and dimensionally accurate. Chamber temperature, greater than 100 degrees Celsius. A heated chamber is recommended because it reduces thermal stress on the part, minimizing the risk of warping or cracking during printing. Always use a hardened steel nozzle instead of a standard brass nozzle. Carbon fibers are extremely abrasive and will quickly wear out a brass nozzle, leading to poor print quality, inconsistent extrusion, and failed prints. Hardened steel offers a balance between durability and affordability. Regularly inspect your nozzles for wear, as a worn nozzle can reduce print quality and dimensional accuracy. Check your nozzles regularly while printing with CF Peak. As mentioned before, carbon fibers will gradually wear down the nozzle's internal diameter, leading to inconsistent extrusion, poor print quality, and even failed prints. Make this part of your maintenance routine. Filament drying. At least 4 hours at 150 degrees Celsius. CF Peak is highly hygroscopic, which means it absorbs moisture from the air. Wet filaments will cause bubbles, steams, and poor layer adhesion. Drying your filament before printing ensures that you will get a strong, consistent print with a smooth surface finish. We recommend using a carbon fiber build plate alongside Vision Miner's nanopolymer adhesive. Carbon fiber build plates offer excellent thermal properties, maintaining consistent heat distribution and making it easier to remove prints without damaging the surface. In our early days, we were breaking several glass build plates a day, printing high-temp materials like CF Peak. Carbon fiber plates are durable, heat resistant, and work exceptionally well with our adhesive. Now, why do we at Vision Miner like to use CF Peak? It's plain and simple. Regular Peak on its own is very difficult to print. That's actually why we're filming this video first and not Peak. It's because the CF Peak parts that we have for this video were done. And now I'm not saying you shouldn't use Peak, I'm just saying that the barrier to entry to getting these beautiful, precise, accurate, excellent surface finish parts is much lower. This stuff is extremely easy to print. As you can see with some of the parts I'm holding here, it has a beautiful surface finish. It's incredibly dimensionally accurate. That's why you're seeing it used on a lot of these demo parts here, where precision and cleanliness is key. It needs very little post-processing compared to a lot of other materials, especially compared to Peak. Peak, you definitely need to be a little careful of with dimensional accuracy. It has a tendency to ooze and it's difficult to extrude, yada, yada, yada. The carbon fiber fill actually makes this extremely easy to print compared to Peak. That's why if you have to use Peak and surface abrasion is not necessarily your biggest problem, highly would recommend that you use CF Peak. There's a wide gamut of high temperature materials that we offer here at Vision Miner, so if you call us, we'll help point you in the right direction. As you can see, there's a ton of different material videos that we have on the channel, so we will find the one that is perfect for you. Maybe it's CF Peak, maybe it's PSU, maybe it's Ultim 9085, but we will point you in the right direction, and if we don't sell it, we'll also tell you where to get it. So now that we've covered what CF Peak is, how it performs, and how to print with it, it's time to put it to the test. We're going to hand things over to Cole, who's going to take CF Peak through a series of tests, pushing the limits of its strength and thermal resistance. Let's see what this incredible material is really capable of.
It's what you've been waiting for, and I have been hoping not to do. It's Peak, not just Peak carbon fiber Peak this time. Peak has a very interesting place in our job, in our heart. What would be a good analogy? They call and they just say, I want Peak, I want to do it in Peak. Why? It's the best. Okay, in a lot of things it is very good. It's also very difficult to work with, very expensive, and just a huge headache. That being said, it do be that way. So we see how good it do be by testing it. I'm going to burn these specimens to see how they behave, put them in a vise and turn them with our digital torque adapter so that I can see how much torque they handle before they break and how they break. Then we have these Z specimens. These will go in our UTM. These were printed straight up and down. We're going to see how much force it takes to break these. The Z-axis orientation is always weaker. And what I'm looking forward to is the XY, because these should perform extremely well. I'm very curious to see the results because, like I said, PEEK is so finicky. If one setting is changed even a small amount, it can change the strength drastically. So let's see how consistent these parts are going to come out. Let's start with the part everyone likes first. Let's light things on fire for science. I will begin, but you can just time lapse this. This is how this works if this is the first video you've seen. Propane flame at full strength, 1 inch away for 5 seconds, and we will see how it behaves. I'll then repeat the test again with the goal of seeing how long it takes before it self-extinguishes. Very similar to PSU. It looks like it is, as we see with these high performance materials, degrading instead of melting. After that 5 seconds, I can't even, wow, that's actually, I can get some deformation. Let me flip this around and let's see how long it takes before it self-extinguishes. I will be capturing the time for how long it takes before it self-extinguishes. 2.5 seconds. Wow. Oh, and while it's still hot, let's see how much I can manipulate it before it sets again. I'll give you a comparison. The GOAT CF PEEK versus PLA. Out. Now, the good news is I don't see a lot of smoke coming off of the PLA, and that's because it's actively burning like a candle. So that's what we're talking about. I always like to use PLA as a comparison, not talking poorly on PLA. That's still burning. Now, just imagine you have designed a part, you're testing it under hood or something that accidentally gets exposed to flame. Oh no, my part is on fire. What are you going to do? Are you going to reach in and try to get it, to remove it, extinguish it? It will, imagine how it feels to have molten hot plastic drip onto your skin. Just visualize that real quick. With most materials, that's a risk. It's still going. We're just going to see how long. I can't get this to burn. I'll do this until it actually melts. See if we can get it to drip like that. That was a long time at 3,600 degrees Fahrenheit. What you'll notice is, yeah, it's all weird and charred up. PLA is actively melting. This just disintegrates. I use a lot of different high performance materials here, all of them. That was impressive. I was impressed with how it handled the flame and how quickly it self-extinguished. This is a very high quality aerospace grade carbon fiber. So this should be very stiff, but also, we'll see how brittle it is. 1, 2, 3. Ow. See my thumbs? Damn, you should, come here. This is wild. Check it out. Don't go for just breakage. Just feel how strong it is first. That's wild. Huh?
Whoa.
I wasn't expecting that either. It hurts.
It does.
You put enough for it. It's so strong that it hurts.
If I
Yeah.
break it.
I'm just going to do it quick. Whoa. That was really satisfying. Yep. It broke exactly the way you want to see parts break. There is no clear failure point. Well, I'm ready to do some torsional testing with our torsional testing tool. PETG was like 5.3. I'm going to say 14. Ready? 1, 2, 3. $13.5. We'll look at all this under the microscope as well, but that is how you want to see a part fail. You would expect with a lesser material to see these break exactly along a layer line. They're printed top, straight up and down on the Z. The whole deal with AM, especially FDM, fused deposition, the parts are weaker. If this was injection molded PEEK, the theory would be that it's absolutely going to be stronger. Why? Because it's one solid piece. With FDM, the weak point is always going to be where the layers interface. What that geometry and that break tells you, FDM is not the weak point here. The fact it's 3D printed is not necessarily the weak point. It broke in a way that would not be indicative of FDM, which would be along a layer line, or this demonstrated no specific weakness. If you showed that break to somebody, I don't think they'd be able to tell that that was 3D printed, is what I'm getting at. It's very strong and it's very well printed. What's that? What printed on what, you ask? Oh, well, that's easy. It's printed on that, the 22 IDEX. By Vision Minor, buy one. Well, I just wanted to bring, you always have good insight, and what are your thoughts so far? Because with the PEEK, there's a lot more testing to do, but.
I'm actually very surprised with how well this did, not because it's PEEK, but because the way it's laid down, because it's FDM and we have carbon fiber in it. I would not have expected the strength demonstrated by this part. Now, we haven't tested PEEK yet. Maybe PEEK is actually going to be a lot stronger, because torsionally, I don't think it's going to be, I wouldn't have expected it to be nearly that strong, because this is, it's shearing along the XY.
You're going to see, I think once we get to the UTM, a more quick and catastrophic break, but instead of it plasticizing, meaning it just stretches out and yields, which I think, yeah, in the XY and the Z specifically, I think this is going to do much better than standard unfilled PEEK.
Yeah. We
started with PEEK. Blah, blah, PEEK is, you know, the OG. But I don't use it a lot anymore because of TPI and Ultim 1010 and PSU and PPSF, all these other alternative materials that I prefer to work with because they are easier to print, they behave better, they don't want to warp so aggressively, and they're just happier at a lower chamber temperature. PEEK requires a lot of tuning to get the part to look good. It'll be strong, but all of these, like you're going to have to really tune your machine and your profile to make them look good. PSU, PPSF, any alternative, man, they just kind of come out of the printer, come out of the nozzle and they look great. You don't have to worry so much about retractions, overheads, bridging. It's also very expensive. That being said, it speaks for itself in terms of its strength and versatility and how well it's performing. Let's get some actual values for that. Now let's break with our fancy machine.
With science.
UTM. So we have X and Y printed flat on the plate, and we also have Z, so it's printed like that. And that's not fun to do, and this is gonna be considerably weaker. I don't know, let's see. There's only one way to find out, and that's to break stuff, but measure it, and that's called science. Off we go.
To the UTM.
The moment we've all been waiting for. Let's see what this thing is capable of. CF PEEK. The XY print, which is going to be the strongest. Let's see how high this guy goes. I'm hoping to break 3,000, and well, we did that easily, ladies and gentlemen. 3,808.0. 3,808 newtons. I was not expecting that. That's incredibly impressive. It is now time to test the Z strength. And, well, I don't have high hopes for this, honestly. Not nearly as strong as the X and Y. That was a performance that cannot be matched, in all honesty. But this is not too bad. 1619 for Z1. Let's see if it can be repeated in Z2. Oftentimes in the Z axis, it's really hard to get consistency between the samples. So let's see how this one does. Any minute now. Still going. Still going. See, this one's stronger. What? This was way stronger. 2231. Now, that's more, and more is better. So, actually, overall, I'm pretty impressed with the Z strength. Now comes the time in the video where we look at this underneath the microscope and investigate the damage that we've done. Now, let's start with the piece that we burned, because I have no idea what to really expect there. I think that this is mostly, I guess the right word would be carbonized. I'm not exactly sure, but yeah. So this did degrade. Wow, I really did some damage to this. Well, let's see what it left behind. Interesting. Well, that was PEEK at one point. let's look at the torsion part. Now, over here you can tell FDM printed, right? But look at the way this broke as one solid piece. That is what you like to see in an FDM print. Excellent fusion between layers because everything looks like one solid piece. This looks like a completely solid piece, which it is, but it was laid down layer by layer, and you can't tell that. But besides the fact that it didn't break along a layer line, it's splintered into multiple pieces. Ah, you can see a bit of layer there. Interesting. I wonder why it... Interesting. Looks like one side of this was further away than the other. Maybe there was a leveling issue. Very interesting. If this was not done properly, if this was printed poorly, you see it break along one of the layers in the Z-axis, but this fractured vertically for the most part. Now for the tensile test bars, let's look at this. Here is our Z-axis bar. Something real weird going on here. I'll admit it. This is a bit more of a disappointing break, to be honest with you. It shows that there was a weak spot here. It just fractured right there. It did split between, it looks like, 2 layers, but still, I would have liked to have seen fracturing, ideally, like this. Now for the X and Y, I'm going to assume it's because there's a gap here. That's why we had failure at this point specifically, right at the beginning of this gap. This is obviously going to be stronger because there's more material, and as soon as we get to this gap, this is where the largest part of that gap is on the very bottom of the taper. So not surprising, but still a pretty good number we got out of that. And finally, here's the other. This is the other torsion part. That's what you want to see. Printed up and down, so like this, but sheared vertically. One of these parts just got flung off, but those two go together. Look at that break. Why is there such a cavernous void here? You see, oh, there shouldn't be these little voids. Was that where there was retraction? Yes, that's why. That's what happens when you don't properly tune your retraction. You're going to get a massive weak spot. Interesting. There should not be these voids here, and they're completely hidden. Maybe I'm wrong here. That might not be exactly what it is, but it sure looks that way. Fascinating. Thank you guys for watching, and stay tuned for more interesting. Let me know if you guys see anything that I didn't catch, which I'm sure you will, because there's a lot going on here. So share that with me, please. I notice we get a lot of people who have a lot of experience in the comments. So by all means, please share, correct me, teach me something new, teach us all something new. And, you know, spread that knowledge. Thank you guys for sharing your comments down below. I learn a lot that I wouldn't normally get just working this job. Thank you guys. Thank you for watching, and stay tuned for the next one.